Hi, this is a thermal camera manufactured by FLIR. It's a model E4. It has a lens at the front, an LCD screen at the back, it has a battery in the handle, all the electronics are self-contained, it's portable, it's light, it's fairly inexpensive, and if I switch it on you can see that within just a few seconds it's operating and can produce a thermal image of my hand. This beast on the bench is another thermal camera. This one is called a NightConqueror and it's manufactured by L3. It's clearly a very different kettle of fish to this one. What I'd like to do today is to explain, at least in outline, what the differences are between these two cameras. And when I've done that, we're going to take the lid off this one and have a look inside it. So to begin with, let's take a look at this from the outside. It's a metal case. The FLIR is plastic and rubber. The metal case is very heavy. This camera weighs in total 48 pounds, whereas the FLIR is only something like maybe 1 pound. Obviously this camera has quite a large lens. I'm going to talk more about that later on. From this side you can see that the casing is milled from solid. Very expensive way of manufacturing things. It's in two halves, large number of screws holding the two halves together. Around the back of the camera here we can see a desiccant plug and a number of electrical connectors. This is the main power and interface connector. Video here. This one is marked test. Really not too sure what that one does. Over here there's an air inlet and an optical connector, which again I'll talk about later, but that's an alternative video output from the unit. The main milled casing that you can see here has an additional metal weather cover over the top. So obviously there are a number of significant technical differences between these two devices. These differences go way beyond just the cosmetics and the fact that the FLIR is portable whilst the L3 is not. What's not obvious just by looking at them is that there's a wavelength difference. The FLIR is designed to operate on a central wavelength of around 10 microns. Now 10 microns is 20 times the wavelength that the human eye is sensitive to. And what that means is that for any given aperture of lens you achieve about 20 times less resolving power. It actually requires a lens 20 times bigger to make a camera operating at this wavelength have the same resolving power as your eye does. In the case of the L3, the wavelength range of this is 3.6 to 5 microns. The FLIR is referred to as a long wave infrared device, whereas the L3 is referred to as a medium wave infrared device. Because of the wavelength difference, the L3 will deliver approximately double the resolving power for any given aperture of lens. Now what's immediately obvious is that it already has quite a large lens. The FLIR has a lens aperture of somewhere around 4 millimeters. The aperture on the L3 is somewhere around 85 millimeters. When you take into consideration the fact that the L3 operates at half the wavelength, this means that it has a significantly higher resolving power. This device is optimized for long range, high resolution imaging. whereas the FLIR is designed for short range, where resolving power is not so important. The wavelength difference has another benefit in that the long wave radiation for which the FLIR is sensitive is also absorbed somewhat more by the atmosphere. The 3.6 to 5 micron wavelength that the L3 is sensitive to will carry much further through the atmosphere. Now the sensor inside the FLIR is an uncooled microbolometer. I don't want to talk too much about how that works, but basically it's an array of temperature sensors. Inside the L3 we have an Indium Antimonide sensor which is cryogenically cooled. This type of sensor is not a temperature sensor, it's actually a photon sensor. This means that it has a much higher sensitivity and it's much faster to respond. This camera is capable of delivering 25 frames per second with ease, whereas the FLIR can't do that. Now this L3 is a sealed, hermetically sealed unit, and this particular one has not been previously dismantled. So in actual fact I'm going to swap to a different one now. So I think it's time to take it to bits. Please bear with me. What we're left with here is the milled casing. I'm just going to zoom in a bit on it. Okay, so the milled casing here, as you can see, various contours have been removed from the case in order to reduce its weight. What we're going to do now is take off the main cover. The first thing that I'm going to do is take out the desiccant. See, that's a cylindrical desiccant holder. It's almost certainly full of silica gel, and it has on the end here it has an indicator of what the humidity level is. Okay, so now we've got the cover off, we can see the layout of the internal components. It's immediately obvious the quality of construction that's been used. Everything is milled from aluminium and the whole thing just oozes quality. I'm going to start by looking at the lens. So the lens here, if I just put a ruler next to it, we can see that the aperture of the front element is actually about 90 millimeters. Now this lens is specified as being a continuously variable zoom from 48 to 342 millimeters focal length and f4. The lens assembly takes up quite a lot of the length of the unit. Now the sensor is right back over here somewhere, and if I lay the ruler next to the unit here, you can see that from the front element of the lens down to the region where the sensor is, it's around 10 inches. It's quite interesting that we see a couple of fans mounted on the side of the lens here. I will show you a bit later on that underneath this cover there's a controller board which drives the stepper motors that are used for the zoom and the focus functions of the lens. I would imagine that they discovered that the heating effect caused by those control components was having a negative impact on the thermal performance of the camera. One of the problems that you get with a thermal imager is essentially it's seeing itself. It sees radiation from its own parts, and in order to achieve the very best possible performance, it's extremely important that you minimize this effect. So if I swing the unit around a bit. Okay, so I'll just point out one or two bits and pieces here. This unit here, this blue piece, is actually a video to fibre optic converter. On the right hand side here we have analog video in, and on the left hand side here we have the fibre optic output. I'll swing it round a little bit more. Okay, from this angle we can now see the sensor in this area here. Now the sensor is cryogenically cooled, as I've previously said. It operates at a temperature of around about 70 degrees Kelvin, which is around minus 200 degrees centigrade. Down in the bottom here there's a compressor unit, and the compressor feeds compressed gas, which is almost certainly going to be helium, into the DUR, and that provides the cooling for the sensor element. Turn her around a little bit more. Okay, so from this angle we can now see the main video processing board. This PCB assembly here contains the circuitry that drives the sensor and processes the video coming out of the sensor. And swing it around a little bit more, and again we can see the front of the lens. And all the time here it's completely obvious the quality of this unit. All of these parts are custom made, it's all milled, beautifully finished, anodized, bit of alachrome on there by the look of it. It's a wonderfully high specification. Now, since this camera is in working order, I've connected power to it, I've stood a monitor behind, and we're going to turn the power on and watch it start up. Okay, so you can hear the cryogenic pump working. And here on the screen we can see that it says the time since start, 25 seconds, and the detector is 11, 12, 13% cold. Detector array size 640 by 512. Interestingly, it says the timing is NTSC. Now I'm going to have to check that, because my understanding is that this particular unit has PAL timing. I will check on that and put some notes on the video. In any case, whilst that's cooling down, let's just talk a bit more about the performance of the camera. So as I've said previously, this camera operates in the wavelength range from 3.6 to 5.0 microns, and it actually incorporates a CO2 filter. CO2 has an absorption at around 4.3 microns, and this has a negative influence on the performance of medium wave cameras. For certain applications it's okay to allow the CO2 wavelength through, and of course you might actually want to observe CO2 distribution, but for this particular camera it has a stop filter in to achieve the maximum possible resolution and distance performance. The power consumption of this unit is around about 50 watts, and it's operating right now on 24 volts. The manufacturer's specified cooling time is 5 minutes, so I'll probably skip forwards a bit on this video so that we can see it working. Okay, there we go, the camera is now working. Let's do something fun. I've placed another lens in front of the camera. This lens has a focal length of about 40 centimeters. It has the effect of a magnifying glass. It shortens the focal length of the main lens on the camera and allows the camera, whilst itself set to infinite focus, via this lens it allows you to focus on something that's 40 centimeters away. So I can demonstrate that by putting my hand in here at about 40 centimeters from that lens, and as you can see on the screen behind, it focuses on my finger. Let's just zoom in on that and do it again. Okay, here we go. Put my fingers in there. There's quite an impressive amount of detail there. There's a millimetre scale on a metal ruler. So the vertical field of view there is a little less than 20 millimetres. The horizontal scale is 25, 26 millimetres, something like that. Quite a fun game. So here's the main lens assembly. Nice big 85mm front element, somewhat smaller rear element. You can see the ring gears here and the transfer gears to the motors that are mounted underneath. I said earlier on these motors are stepping motors. In actual fact that's not true. The motion of them is extremely smooth, and they can't possibly be stepping motors. I think they must be AC servo motors. And here's the control board. It's interesting that it's not fully populated. There's obviously another version. And as I turn this ring gear, you can see the lugs here that are moving internal elements of the lens, one going backwards, one going forwards, and it's just a beautiful smooth motion. And at the back here there's a similar arrangement with a lug and a helical sleeve, and as we turn that you can see this element here moving in and out. And that's the focus. There's a end stop detector here, and it looks like another one just here. Okay, so in a way this is the business end of the camera. This is the MWIR assembly, which contains the infrared sensor. Here we can see an interface board. We can see the metal pipe that connects the pump to the GWIR. And on the front here we can see a mechanical shutter arrangement which is gear driven from another AC servo motor. Just here we can see the vacuum seal or the pressure seal on the GWIR. I'm not sure what kind of pump this is, but this appears to be a control box. On the end of the pump here we have the manufacturer's information. And we can see a temperature witness sticker there, 93 degrees C, which doesn't appear to have been triggered. And here we have the power supply board and the main processor card. The power supply board has a couple of DC-DC converter modules on the rear. These are the connectors that are seen on the rear panel of the camera body. And there's a variety of devices on the processor board, a Siemens 16-bit microcontroller there. You can see the crystal, that's flash memory. And in this area here we have a couple of RS485 interface chips, some UARTs, various other bits and pieces as you'd expect on a small processor card. I've noticed something quite interesting about the design of the lens hood. So the lens hood here has an aperture in the front just under 90mm diameter, and that's about the same size as the front element of the lens. We've got a diameter there of about, just under 90mm. And yet this lens assembly is mounted inside the casing, and it's around 13 centimeters behind this aperture ring. I find that very interesting because when the lens is set to its telephoto setting, it has a field of view of about 3 degrees. So if we imagine a beam of light coming in here from 1.5 degrees offset from normal, you can imagine that there is not much scope for vignetting to occur. The light can come through the front here and reach the lens because the beams of light are entering very close to the normal. However, when the lens is set to its wide angle setting of 48mm, it has a 21 degrees field of view. Now this is a different situation. If we imagine a beam of light coming in 10 degrees off axis, there's potential for quite a lot of vignetting to occur. It's difficult to imagine being able to observe a 20-degree field of view from back here without the effect of looking through a sort of a tube. Now I'm going to have to do some tests to prove this, but I suspect that the presence of this aperture ring on the front of the camera tells us that the application of this camera did not cater for use of the lens at its wide angle setting. I rather suspect that it was designed to be used for long-range telephoto purposes only. I'll do some more tests and see if I can find out. I hope you found some of that interesting. I've already posted a few quick demo videos of things like horses and rabbits. I'm hoping to do a few more of those over the coming weeks. In the meantime, thanks for watching.